as soon as I made the first public release, people said, "Hey, that looks a lot like MATLAB. Can you make it more like MATLAB?" Like, because if you would just make it a little bit more like MATLAB, then I could take my code and give it to my colleagues who use MATLAB, but I could use it in Octave, and I wouldn't have to make any changes. And I said, "Oh, I don't know. There's some things about MATLAB I don't really like. I think that some of the features are bad. You probably don't really want to use them." "No, we really want to use them because we want to be able to share code with our colleagues who use MATLAB." And so I was very reluctant to give in to that for a long time, but there was a lot of pressure, like immediately, from people. They wanted MATLAB. And a year later, I had version 1 of the software and actually made a bigger announcement. Got quite a bit of interest in it. And it took another 8 years for the book to finally be published. So the whole reason that we started working on this was to support this textbook, and the textbook didn't appear for like a decade. But Octave was being widely used during this whole time by people all over. We made it free software so that we wouldn't have to include a diskette in the back of the book. We realized that diskettes in the back of the book were already obsolete when people were doing that, and that downloading from the internet was the thing to do. And this was before the internet. This was before the term open source had been even thought of. People were, there's a GNU project and free software and all of that was around, but nobody was saying open source. Nobody was worried about the development model of open source. There was no, I don't think I even used CVS as a version control system. I used RCS to start this project. And there was no Git, there was no GitHub, there was none of that. The web didn't exist. FTP sites were the way to distribute software. The book has gone through several editions now, and in 2017, I'm still working on Octave, which was a big surprise to me. I didn't think it would last. I thought the project would last maybe, a year or two, I'd be done. And actually, in version 1, it was a couple of years, and I had something I was happy with, enough to release. And earlier this year, I joined ESI, which I think is going to bring a lot more resources, at least for me, to continue working on Octave. And the Scilab project joined ESI earlier in 2017, and I think that we have a pretty bright future. So to move forward a little bit. So people often say, "Why did you call it Octave? What does that have to do with it? Is it about music?" And I say, "No, it's not about music." When I was an undergraduate, I was at Oregon State University, and Octave Levenspiel was a professor in chemical engineering there for many years. And I took a course from him. He doesn't remember me. Well, when he was still alive. I found out later he didn't really remember me as a student, and but he made a big impact on my life because I could see when he would solve problems, he could just sort of think about, okay, the order of magnitude of this physical constant is this, and he knew the equations behind many different things, and he could just sort of go to the chalkboard and write out, well, I think that this process might be possible. It would be worthy of further study. We could actually do more detailed calculations later, but I think if you think about this, it's going to take about this much energy. Is that reasonable or not? And he could do these quick calculations like that. So I thought, we had this 5-minute conversation, Jim Rawlings and I, about what are we going to call this software. And since it was a reactor design textbook, which is what Octave worked on, he also wrote a famous chemical reaction engineering textbook back in the 60s. And so I said, well, what about Octave? We'll call it Octave. And we didn't really put a lot of thought into it because I didn't think it would matter. This software was just going to be with the textbook. It wasn't going to be used by students. It wasn't going to be, I had no idea what was going to happen. So that's how the software was named. It has nothing to do with music. It's all about Octave Levenspiel. And so what was I trying to do in 1992? This is not, the point is not to try to read this, obviously, but I made a photocopy of the function reference, the list of functions that were available in MATLAB, like one of the first PC versions of MATLAB. And this was in the back of the reference manual. And up here it says, this is a list of all the functions in MATLAB. Okay. So I thought, well, if we get most of those functions,
200
then,
maybe,
then we,
200 functions.
Then we probably have pretty good coverage, because if that's what MATLAB has, then if I can do the equivalent functionality of this, that's probably a pretty good set of tools, right? And I highlighted them as we got them, okay? And you can see that the difference in color doesn't mean anything. It means I used a different highlighter at a different time, and it faded differently. But I said, well, I have pretty good coverage. This was probably about the time of version 1.
You did a pretty good job.
I thought we're done,
yeah.
right? There's nothing left to do. Now, if you look at what is the scope of the project today? Well, I mean, there's several thousand functions in core MATLAB, and there are many, many more functions in the toolboxes. I mean, it's a huge, the scope of this software has grown in the last 25 years tremendously. So trying to be like 100% compatible with this thing, which isn't defined by any standard, is virtually impossible. Okay, but we're still trying. So the early goals were just to have an interactive language, make it freely available, and have access to high quality numerical tools. Right, that was it. That's all I cared about. Today, it's obviously, like I just explained, the users have come to expect a high degree of MATLAB compatibility. They want their software to just work. If they've written it for MATLAB, they want to put it in Octave and it just works. They want it to be easy to install and easy to use. And I want to make sure that the community of Octave contributors and users is active and healthy. I used to think that the Octave project was okay, but it wasn't really all that spectacular. But then I learned a few years ago that the median number of developers on open source software projects is 1. Okay? 1. I know, right? It's pretty funny. I mean, people start a project on GitHub or SourceForge, and they work on it by themselves, and maybe they get a few users, and then that's it. There's one person working actively on the project. Maybe they get a few contributions back, but that's it. And then they probably give up their project. So if you have 5 or 10 developers who are actively making contributions to your program, you are pretty successful. And Octave has, in any given year, because I look at these things periodically, probably I think 50 or 60 people have made changes to the core Octave code. I'm just talking about core Octave. Then there's a whole set of packages that there are many, many more people working on. But core Octave gets maybe 50, 60, 70 people, and any given year make at least one change. There are two of us who make the majority of the changes. Okay, and we're making say 500 changes every year, and then it drops off really rapidly. But we have 15 or 20 people who make half a dozen or more changes every year, and that's pretty healthy project. And we have very active. It used to be a very active mailing list, but it's funny because now mostly what happens is people discuss things on the bug tracker. Right? And because it's better, really. I mean, we used to track bugs only on a mailing list, but that was terrible. So now we track bugs, with a web-based thing, and much of the discussion happens there. And then we have a fairly active community developers who are chatting all the time on IRC, and it's It's really great because we have yearly meetings. The next one is going to be in Geneva in March at CERN. So it's open, it's free registration, but we would like people to actually tell us that they're really going to go because there's limited space. So we don't want like hundreds of people signing up just thinking, well, maybe I'll make it. But if you can, that would be great. We can move on. About compatibility, and versus innovation. So people sometimes ask us, why don't you there are some features in MATLAB we don't really like, or maybe we could do better. Can you maybe could you do something like this new feature? It would be really awesome if Octave could do this. It would really set it apart from MATLAB, really make it great. And it's true, some of those things would be great. But these are some examples of things that have been done in Octave before they were done in MATLAB, and they cause trouble every single time. Because the features in some way were introduced later in MATLAB, and the users demanded not the feature, but the compatible feature. And in some cases, those features were conflicting. Both could not exist at the same time. So in order to have compatible code, we had to actually throw away the innovation. So this has happened enough times now that when somebody comes along and says, well, it would really be great to have this new feature that's not in MATLAB, like a language feature, a syntax, change in the syntax, some sort of fundamental thing, not just like it would be great to have this package of functions, but change the syntax so we can do this. We have to say no because it introduces a risk for the future of we'll have to redo this or throw it away because there will be some time where there will be an incompatibility in the future. I introduced these fopen and printf kind of features in Octave before they were in MATLAB, and I did it slightly different, right? It had to be changed over time to be compatible. I had variable argument lists that looked like the C style variable argument lists with ... indicating extra arguments that aren't named, and then I used a function to get them for you. And then MATLAB, they introduced vararg in and vararg out. So okay, now we have two ways of doing this. Do we support both? That's a cost. Or do we just throw away the old thing and go with the compatible one? Well, that's what we ended up doing eventually. I had data structures before MATLAB did. They did it differently. I did short circuit operators before they did. They did it differently. They finally came around though and realized that their way of doing the short circuit thing was probably not the best idea.
Maybe they took some inspiration from what you did.
Well, they actually had users tell them that wait, there's some real fundamental issues with the way you did the short circuit operators. They overloaded the single bar and the single ampersand to which were element by element or an and on matrices, but they made it so that those operators only short circuited inside the condition of an if or while statement. And if you move them outside, they did not. And this has I said, well, wait a minute, that means that the behavior is going to be different if you call a function either on the one side and it has a side effect, because it won't be called inside the if or while statement, but if you just move that out and assign it to a temporary, now it won't short circuit and your side effect will always happen. Well, that's bad. And they said, no, nobody will ever do that. This was on the mailing list, or the MATLAB news group way back in the 90s. And finally, somebody came along and said, oh, but wait, look, there's actually, the behavior is different with empty matrices involved in these operators. He said, oh, that's bad. So then they actually went and said, and introduced and or in a slightly different way from Octave, but it's very similar now. And then they encourage people not to use the single bar, but they still allow it. They didn't stop. So, and then multiple functions in a single file. I introduced in Octave the ability to define a function on the command line. and also the ability to put multiple functions in a script file. You had to define them at the top of the file first, but they actually, once you ran the script, they were just defined in the global namespace. Okay, I don't know if that was a good choice or not, but that's what I did, and it worked. People liked it because they could define a script file that had a whole bunch of functions in it, and then did the calculations at the bottom, and they were happy to just run those scripts and like get the answers. MATLAB didn't allow that, but then they introduced like sub-functions. It's like if you had a function, you could have sub-functions. And then they said, well, maybe we want different scoping rules. So they had nested functions. And then they introduced like class def, the object-oriented thing, and recently added the idea of local functions. They're outside they're not member functions. They're local to the class structure. They're defined at the bottom of the file. And then they said, oh, we could probably do that for scripts too. So now if you have a script that runs, you can define functions that are used in that script, and they're defined at the bottom, but they have scope that's only inside the script. Okay, they're not visible outside. So this is incompatible with the way Octave's local functions or functions in a script file work. But, and it's going to create a problem for us in the future because we can either do, you can do one or the other, because the way that their local functions work, that since they're not globally visible, they're only visible to whatever happens at the top of the script. It's like once you've run the script, those extra functions you defined at the bottom are not available at the command line for you to call. Okay, like they are in Octave. So that's a little bit of different deal. So we're gonna have to face, like, how do we deal with that incompatibility issue at some point? All right. So things are gonna happen in the near future for Octave. More improvements in the usability and reliability of the GUI interface. People really like the GUI. They really want to be able to like point at a variable and edit it like in a spreadsheet-like thing, and look at, like, if you have a complicated structure with the cell arrays involved, they want to be able to click on those things and look at that graphically, you know, in a spreadsheet layout, rather than having to type those things at the command line and try to view them. Other improvements to language features and compatibility, like I mentioned, class def is this object-oriented thing in MATLAB, and it's partially implemented, but it's not complete, and people like that. It has implications for us as well, because for compatibility with MATLAB now, because MATLAB has internally they're using class def objects all over the place now inside MATLAB. So to be compatible, we have to be able to do the same. So our class def implementation needs to be complete. Packages, which is another namespace control thing in MATLAB, it's partially implemented, and that needs to be completed. And then MATLAB for a while now has had their latest mat file format for saving data and loading data back into MATLAB is based on HDF5, and we are not compatible with that. So we need to fix that, because it will allow us to save large data files. And a much longer term goal is a JIT compiler to make the overall speed of the interpreter fast.
On those both aspects, maybe it's also worth mentioning that, well, in Scilab, we've been working on the HDF5 file format for saving. So this is probably somewhere where we can collaborate with the Octave project.
Right.
This is interesting, and also the JIT compiler, it's something that we've been working on for quite a long time, and I mean, we also see some long-term potential in doing that. So okay. Do you have more slides? I think this was the last one, right? Oh, toolboxes. Yeah. Oh, so important subject.
Beyond core Octave, the other thing people really want is to have more complete coverage of at least popular toolboxes. And I'd say that the most widely used ones that I hear about all the time are these. Everybody has their favorite one though, so there are many in MATLAB now. This is a kind of a tough area, because I don't think there's any one person who can be an expert in all those areas. and these are so implementing any one of them requires quite a bit of domain-specific knowledge, and so we have, you know, and they're quite large now. I think I took a look the other day, and just by going to the website and looking at the list of functions available in each of these toolboxes, you can do the same. I think if you add them all up in this collection here, it's about, like, I don't know, 1,500 functions.
Yeah, it's a lot.
So that makes that slide earlier, what I showed with how many functions are available in MATLAB in 1992. Like, that looks trivial, you know. You could do that in a week, but this is like a much larger thing. And like I said, I don't think there's nobody who's an expert enough in all those domains to do all that. So that's a large team project. So
maybe it's worth asking also here if some of you use some of those toolboxes to know, well, also because it's one of the good things to have a feedback of the community who's using what in order to, you know, prioritize this work. So you guys use signal processing, some of you here?
I try to use image processing.
Okay.
Yeah, and first of all, I think it will be very popular, because when my company pay 7,500 for MATLAB with image processing, it's terrible. Yeah. And what's about image processing? But I'm not satisfied. I tried it 3 years ago, because I cannot read it. I cannot read image. For example, first of all, I have to read JPEG image.
Right.
But you wrote that it's possible only in Linux or something like that, and you have some special standard. In any case, I have a failure, yeah, and stop it. Yeah. But my comment, it's good that you do that image processing, but really what we need is not an image processing, it's in the core, Scilab and MATLAB. We need 3 functions. First function, read JPEG and DICOM files. It will be enough. Other, I can write, read and write myself, read and write that files. And second, show, image show. I think if you add it to the core, 3 functions, it's make, for example, my life as an image processing much more easy. I do the rest myself. Yeah,
because those are arrays, basically matrices that you can work with afterwards.
But if in addition you add 1 DIM and 2 DIM convolution, I will be the happiest guy.
We take that into account, okay.
That's it.
And I think that's what MATLAB does in the core MATLAB, right? They have this read and write. It's in the core MATLAB right now. I think it is.
I don't know, but yeah, there's also we've discussed these are currently packages that are external, but we've talked about including them in core Octave in some way, just having them so they're always available for all versions for everybody all the time, rather than having you to, you know, asking you to go get a package just to do these core kinds of things.
In our company, we try to use MATLAB for image processing, wafer scanning process. So basically, the wafer is scanned through a laser beam, plasma beam, and that is got deposition. So there is the image of non-uniformity of the deposition on the wafer. Think about a T-scan, there is a non-uniform deposition. And from the image, basically we get out a function how the non-uniformity is and wrote an inverse function so the speed of the scan should be so that the deposition is uniform. So that worked actually kind of well and not too good. But
okay. And so far you're doing it with MATLAB, but
so far.
Okay. Maybe it's worth investigating. Okay. Okay.
So that's really all I have.
Yeah.
I mean, but I'll be happy to answer any questions.
Okay. Well, thank you, John, for sharing that with us. We have a few more presentations afterwards, but if you want now to ask questions more specific to Octave, and we can go on afterwards with the agenda.
Are there any questions online from people joining us?
No. All right. So I guess we'll.
Watch out for the sound.
Yeah.
Move your computer too much. Maybe increase the sound.
All right. So we'll proceed with the second presentation, and it might also answer some of your questions, because I mean, you guys are here and you figure out, well, why is Scilab and, you know, like now with Octave, now what is going on? So we'll try to answer some of those questions. So this is the second presentation that we want to hold this morning, is on open source and, wait, yeah, it's coming up. Open source and cloud platforms for the development and deployment of scientific and engineering applications. So, so this is the second slot in the agenda, and afterwards we'll go through some industrial use cases, technical insights, and, well, feel free to ask questions. Here I'm going to go also in a demonstration, some demonstration in this part. So yeah, it'll be pretty interactive. It's just like as a teaser to start, just to show you yeah, a few areas where Scilab is being used at the moment, from the French Space Agency for flight dynamics, from Dassault Aviation. So you see most of those examples, they come from French company, because, well, you probably heard it. We from the Scilab team, we are French. And so Dassault Aviation is also doing some data analytics for aircraft design with Scilab. There's an Italian oil and gas company doing system modeling, because as you will see afterwards, also we have an alternative to Simulink. There's a German aerospace company, German Aerospace Center, DLR, doing a control system with our alternative to Simulink. And Sanofi, a French pharmaceutical, French and international pharmaceutical company, developing an application for energy optimization and deploying it on the cloud. And the French Research Institute, CNRS, is performing signal in image processing. Here it's for the detection of archaeological sites. So they're flying over France and just trying to detect some archaeological sites. Quite, yeah, original, let's say. So first an introduction, a few highlights. So Scilab and Octave, well, you all know that are competitive with MATLAB, but open source and free. As I mentioned, in Scilab itself, we have an alternative to Simulink called XCOS for the modeling and simulation of control systems. Scilab has a quite wide community. We record every month around 100,000 downloads worldwide. So, I mean, most of them, I mean, 18% of them are coming from France, because as I mentioned, and you will see in the history afterwards, the Scilab initiative is coming from a French research institute. But after that, USA, India, Brazil, Japan, China, and Germany are like between 10 and 15% of the downloads from Scilab. So we don't know like really precisely, because, you know, like open source, so you can download the software and deploy it to as many people as you want. Also, we don't know much from Linux distributions, because, well, you do just apt-get and you get it from the your distribution, if it's like Ubuntu or Fedora, and so that we don't track, obviously, but from our website, this is the numbers that we have. And before joining ESI, now as part of a ESI solution, we developed a cloud solution to deploy application securely on the cloud. And I'll show you a demonstration after that if you're interested. So a bit of history also. So now I try to take some of what John said and summarize it in one timeline. So in early 80s, there was a free version of MATLAB developed in the public domain and financed by the US state. And from this, basically, there was, well, different development projects. So Scilab was started during this time between the 80s and the 90s in RIA. It's a French research center for basically for computer science and control systems. So this is what it stands for. And so in 1994, at the same time, basically, the first version of Scilab was released independently from, well, the first release of Octave. So 2 projects started, and well, today I'm actually quite excited by the fact that it's actually the first time that we are in the same room and well, talking together about the future of what could be an alternative to the big M.
Yeah, I would say at that time, I'm not sure that either one of us knew about the other. I mean, this is before Google, right? So, so the only way you would know about this, maybe you would see an email announcement about, like on some numerical analysis or in a news group or something. You say, oh yeah, oh I see, there's something else to do. And you find the FTP site, but that was about it. There was no way to search. And Scilab and Octave were not the only 2 array-based languages that were developed around this time. I remember, like, there was one called RLab, there was one called Yorick, there were several others I can't remember the name of anymore. And they were all those one developer projects. Like, there was one guy, he started RLab, and he worked on it. He actually got quite a few followers, but its syntax was not compatible with MATLAB. And people thought it was really cool, but it wasn't compatible. Yorick was I think their focus was more on tensor calculations. Like they had ND matrices before anybody else did, before MATLAB did, before Octave, and they all died.
So there's just the 2 of us now. I mean, in terms of projects, there's many more developers, but
all the free software projects that I know of that were array languages, other than these 2, are kind of dead now. There was another one that developed, like, even more recently, called FreeMat.
Yeah.
Which actually aimed at MATLAB compatibility, but it was another project that was mostly one guy, and I think he's lost interest for the most part, which is not surprising because, I mean, if that's your aim and you're one guy to try to do this, it's like,
yeah, compared to a $1 billion company, it's pretty tough to follow on that.
It's not a weekend. It's not something you do on the weekend anymore.
Not really.
Yeah. Sorry.
No, it's all right. And so our small experience of an alternative was going through the French research, and we created a consortium in 2003 with some industrial company in France, also research institutes such as a company such as Airbus, Peugeot, the French automotive constructor, and so the French Space Agency, and so on. So, well, we tried to put together this consortium, and actually what they ended up willing is to have some support, basically, and that's the reason why in 2012 we created the company Scilab Enterprises as a kind of a spin-off, basically, of the research. For this whole time, it was more of a research project, and we figured out, well, in 2012, so the product was getting quite mature, and now what was needed from the industry was some support in terms of training, like support, like Red Hat is doing, basically. And specific development. So we created Scilab Enterprises. So today we're around 10 people, and we joined ESI earlier this year in 2017. So, and I guess I can tell you also a few words about ESI because, well, today you are at ESI, and I want to introduce you, also the reason why we are at ESI. Basically, ESI was founded in 1973. And they were focusing in the first place on simulation and virtual prototyping. One of the first subjects that was addressed was automotive crash simulation. And from that, they went into a lot of different domains on simulation and analysis. I will show you another slide afterwards displaying all of the products. But here in the latest year, from 2012, they started to acquire company and develop themselves in the direction of numerical analysis, and open source is one of the aspects. So in 2012, they acquired the company behind the software OpenFOAM. So maybe some of you know about OpenFOAM for computational fluid dynamics. So it's a large and quite famous software for fluid simulation. And so basically, ESI acquired the team behind and is supporting, keeps on supporting the development of the software. So and in 2017, well, the acquisition of Scilab is going in this direction of providing alternatives to only proprietary software. And so today, those are all of the domains where ESI is active. So in virtual manufacturing, in virtual performance, so meaning simulating a system from the mechanical point of view, the vibroacoustics, electronics, and CFD. We have a lot of people here also from the several ESI teams that are in this domain. So if you do have questions, you can talk to them afterwards. And we are now, the Scilab and Octave teams are in the systems and data analytics, basically. So, and yeah. So about ESI and now open source numerical computation. So why is ESI investing in open source? I mean, for software companies, that's always a good question to ask. So basically, what ESI figured out is that the software that are being used in simulation are used by mostly by experts. So if you look at a big industrial company, there might be only like 10 or 20% of the engineers that are using simulation software, and there's a huge potential to reach the other 80%. And basically, those other 80% of the people, they use either MATLAB or even worse, Excel. So there's like a huge amount of people that you can reach with open source software and just numerical analysis, because basically numerical analysis is at the basis of developing a mathematical model and afterwards build simulation. So this is the reason why. And now in relationship with Scilab and Octave, basically, so ESI is willing to continue fuel the open source development of the software, to propose also, here I think it's the following slide, it's over here, to propose also services, professional services, in order to have the industrial company switch, have an alternative to MATLAB. And yeah, so compatibility for that is a key aspect of success. So that's the reason why also John joined us, and now with Octave. So from the high-level point of view, what we cover, and this might not be new for most of you, but I just want to summarize what Scilab and Octave cover in terms of functional domains. So the first one is modeling and simulation. What we mean by that is starting by a mathematical based model, and generating data, performing visualization, optimization, and code generation, more specifically in the case of like for embedded systems. And the second aspect is the scientific data analytics. So starting either from the data, simulation data, or experimental test and measurement data, and going back to the model with machine learning methods, for example, or so-called model reduction methods performed on simulation data. So basically, and the idea is now to loop. Also, that's one of the concepts of ESI is to go back from the data to the model. So I know that maybe some of you have heard here, especially in the Bay Area, of Octave through a well-known course on Coursera on machine learning. This is a subject that is quite hot at the moment. So we are trying to keep up with it, but I guess this is going to be also one of the focus for the future. And on top of those two domains, there's also something that we see with our customers is that they tend to develop application. And what we mean by application is to develop not only the algorithm, but separate them from the data and from the user interface in order to have, in the end, a complete package application that they can share with their colleague. And through this user interface, they don't need to go in the code They can just, fill up a form and see the graphs and so on. And so this is something that is actually really valuable to the end user in the end. So this is something that we want to ease. And that's, well, I will show you some example afterwards. That's why we want to focus on this development and deployment. And that's also the reason of the cloud offering on top of that. So yeah, and here talking about the ESI Cloud. So basically, we started to develop that in the Scilab team as a way to, deploy an application that you develop in your numerical tool. So as I mentioned, you develop your algorithm, you develop your graphical user interface, and when you upload it to ESI Cloud, basically what it does is, if you have an interface that's producing a web app directly, and I will show you afterwards how it looks. And if you don't have a user interface, if you just have an algorithm, basically it's becoming a web API, so web service that can be called by another machine, integrated in an enterprise solution. So yeah, this is the idea behind the cloud offering that we are putting together. So it can run either on public cloud, but also on private cloud. So, for security issues or confidentiality. And yeah, I guess, I mentioned that, but it's like kind of a conclusion slide on Scilab and Octave in ESI Group. So as I mentioned, professional services, cloud offering to deploy applications, and also software solutions, like also coupling it with other ESI software. We've been doing that and working with, for example, with the CFD team on like performing pre and post processing, design of experiment, like to explore the design space, and yeah, building also application on top of those solutions. Know that there are some people in ESI that are developing some application with Scilab. So yeah. So do you have questions so far? I wanted to go into live demonstration now, but before that, do you have question? Later. Okay. Let's go through the live demonstration. So what I wanted to cover in a few minutes, it's just, go through like this modeling and simulation, develop an application, take an example, develop an application, deploy it on the cloud, and also deploy an algorithm. So the first one is, and I took the example of an automotive suspension system. So basically it's a linear equation, a second order linear equation. So maybe some of you have already solved this by hand during your studies. So basically here's the idea is to use the ODE, the ordinary differential equation solver. Well, this I did it in Scilab with a Runge-Kutta solver. And well, I'm just gonna go ahead and show it to you. So this is Scilab, for those of you who come from the Octave world. And well, it's not, I guess it's not that different in philosophy. So this, I'm gonna start with a file browser. I'm just gonna go in, no, this was not it. In Google Drive, and my demonstration, and the automotive suspension. So yeah, I can just open this Scilab script, and it's opening it up in, sorry for the German words. I can this is the Keynote, this is our editor, so I can just plug it in here and simply play this script. So what it's gonna do, it's both a graphical interface, but also is a linear equation solving behind. So when I click on it, it's just basically solving this linear equation with a step function as input, and like as you can see, it's mirroring the behavior of a second order system with a damping. So this is basically what you can do with the Scilab language or Octave language. All of those numerical tools are really good in order to solve such kind of problems. Now, what I want to show you is with Xcos. So basically, Xcos, as I mentioned, is an alternative to Simulink, and what it's enabling is a block diagram. So here I'm going to take the same kind of example as before. It was a quarter car, so now I'm putting 2 quarter cars, so it's making a half car with a front suspension, here the rear suspension, and basically it's enabling to run this whole simulation as a system diagram. So this is XCOS, and well, basically here, if I just play this, what you will see, I have as an input here, you can see the step function from the road, and this is the displacement. I think it's not the displacement; it's z dot. It's the speed, basically. So it's just a derived function of the displacement on reacting on this step function. So yeah, this is XCOS. So this was for like modeling and simulation. Now the second part is more on data analytics. So what I'm going to do is just like show you how to import some data from Excel. Those could be like experimental data. You make some experiment and you just try to fit some model. So here the models that I'm going to fit is exponential of cosinus and sinus. Doesn't mean anything. I mean, it's just an example. And here, basically, the three parameters that I want to define and to find through this optimization problem, those are the C1, C2, and C3. So let's go in Scilab and open this XLS file. So what I'm first doing is basically I'm opening this file, reading it in Scilab, and I'm going to plot it. So yeah, here we go. So those are the data. What do I do with that? I'm going to put it in here. Okay. And now what I want to do is I'm going to define this function and define also a cost function. So basically the cost function is what I'm going to try to reduce in this optimization problem. So I'm just going to take the value of this exponential function and try to compute the difference with each and every one of the points that I measured. So I'm going to do that and use the function data fit and represent it. Yeah, here you go. So there's just one run right now of the function. And as you can see, it does not give me that good of a result, right? I mean, and in the optimization problem, what is really important is to select a good starting point, basically. So what I'm going to do here after doing that is, well, I'm going to delete that. And I am going to, iterate. And I'm going to do like 100 iteration, but changing the starting point between A and B. So A is -5, B is 5, and I'm going to just take a random iteration on that and try to find the best value for this problem. So it's going to iterate 100 times, and in the end, it's just going to pick the best solution for my problem. So it should be fairly fast. So there's different kind of, here what I'm using is a data fit function, but there's a lot of optimization function in Scilab. And what we figure is, yeah, you see, it's giving you afterwards a result. It's quite small, sorry, for C1, C2, and C3. So here, basically, through this script, you can solve such kind of problem. So this was for data analytics. And now what I will do is I'm going to take a small example of a weather forecasting problem and develop an application based on that. So let's go back to Scilab and solve this problem. So first, what I did is I got some sensor data. Here, what I can do in the first place in my console is to read those CSV data. Sensor data. Okay, I'm not gonna play that. So here you can see it in the variable browser. So here I can introduce you to this variable browser. I can double click on it and it's opening up a variable editor now. Sorry, it's in French. There's also an American version, like an English version. Don't worry. And here I'm going to select the 12th column of those data. Those are, if I plot it, those are pressure data from some sensors. So here, like simply through click, I can display my data. Now the second thing that I want to do is I want to use the Scilab language in order to represent linear regression on those data. So nothing fancy, just a linear regression. So what it does, it's taking just the same way as I did the pressure, performing a linear regression on those data, and just plotting it. And so this is from the algorithm point of view. Now, what I want to do is when I develop an application, I want to develop also a graphical user interface on top of that. So this is basically it's working in Scilab. It's through the same function as in MATLAB, UI control. And well, when I play it, basically you will see it's just displaying a very simple interface with a button. Call my script, so it's push button, it's calling my scripts. When I click on it, it's just calling the scripts that I developed. But so it's not very elaborate, but it's just to explain how the complete idea of graphical user interface is working. And so once I did that, what I'm going to do is I'm going to load the complete. Yeah, I was just worried that there might be a bug. By the way, I'm using the latest 6.0.1. It was just released this morning by my colleagues in France. So
I told him that was very risky.
Yeah, and I like the risk, and I trust. No, I trust my colleagues. They are really talented. So, so here, as you can see, this is like a complete application. Like it's very small, but complete application on weather forecasting. So I can, as I did before, build a regression, use a slider in order to select the time period where I want to perform this linear regression and validate the trends. And I can do the same for temperature, wind velocity, and so on. So basically, this is the idea on application development. Now, what I want to do is I want to deploy this application to someone else, someone who's actually not using Scilab, like not using such numerical tools. So this is what I'm going to show you now with the cloud. And so here you go. So here I am an administrator of Scilab. Well, it's Scilab Cloud. It's we developed it before joining ESI, so it's still called Scilab Cloud. So what I will do is, as an administrator of this application, I'm going to create a new account for a user. So the user is going to be called Yann Debray, so that I can have access to it. And I will give him access to this weather application that I uploaded, and I will give him access to 2 groups. And basically here the groups are mirroring the different sites. Here it's in Corsica. If you know about Corsica, it's Ajaccio and Bastia. So it's a really nice, cute little island in France. So here I just created a new account, and I will receive, I just received an email, so from Scilab Cloud, to set up my password. So I'm going through the whole process of showing you how to deploy an application. Now, this I'm going to shut it down, and I'm going to choose myself a password. I'm not a robot. Update. Okay. So now, oh no, this is not the right account. Now I need to, log in with this new account. So basically, now as a user, my administrator just gave me access to this weather application, and I'm logging in. I don't need to have anything installed. It's all in the cloud. So I can access this weather application, and you will see it's basically looking like just the same. It's the same code that I uploaded, and now on the cloud it's producing a web interface, and you can like use it, and it's interactive. The data are located on the server, so there's also everything is centralized, the code and the data, so that you don't have to deploy on every single machine of the end user a desktop application. You can, everything is centralized, the code and the data. So it's easier for the IT, for the deployment. If you make an update to your code, you can just push it, and then the user, it does not have to download a new version. It's already accessible through the browser. So it's really handy for the sake of deployment. And as I mentioned, also for the data centralization, what's good is that here, for example, I have people that are accessing only to those data, and they are, afterwards accessible to everyone who has access to those two groups, Ajax and Bastia. So yeah, that's it basically. And yeah, that's it for the demonstration. Do you guys have questions on those aspects of what I mentioned so far?
So if there is no internet connection,
no
nothing
cloud.
works.
No internet, no cloud.
and when a connection back, so which version? They will have the latest version from cloud. If they open, they will be the latest version.
Yeah, I mean, otherwise the other way is to go through a private cloud, like deploy it internally on an internal network.
Mm-hmm.
And this way you don't have those problems. Obviously, afterwards for updates, it needs to go through, us to update the cloud. It's new functionalities that we develop on the cloud that needs to be pushed to this private cloud on a private network. So yeah.
Did you do the deployment also? I mean, you showed how to give someone access to the code. But I don't
know. I know I skipped this part, but it's true. I mean, here I can log out from this user account and go back to my administrator account. And if I show you here in the settings as an administrator, I have administration tools. So I went straight to the user creation, but basically here I have access to the application. Here the weather application. I can modify how it looks like and update, upload new version, production version, but also development version, to iterate on different versions that won't be visible to the user, and afterwards choose the one that is online, and I can upload it from Git or archive. So yeah, I skipped this part. It's true, this is the only part that I skipped in the whole toolchain.
It's like WordPress for
WordPress for applications.
For scientific applications.
Cool.
Yeah,
I like this. Yeah. This is great. So and this is the kind of thing that we can add this, or I think we can add the functionality for Octave pretty easily to this as well, right? So this isn't really specific necessarily to Scilab so much as the whole managing those files and what happens when you click on them.
Exactly. Yeah.
It runs Octave instead of running Scilab. It seems to me that's pretty much it. So
that's something that we plan on doing for the future. Because I mean, if you could just upload your MATLAB file and and produce an application, I guess that has a lot of potential.
So I like this idea because if you've ever tried to deal with people who aren't, they say, I'm not a programmer, right? I don't know what you're talking about. I can't do get. I can't do get either, but I can't do that stuff. That's too hard. This gives them, and then they've written applications that rely on, like, okay, if it's Tuesday and you're in my home directory, everything works. But if it's any other day of the week, or you are trying to run this on your own computer, you're out of luck, right? So this gives them, this sort of forces them to put something here that will work for anyone, right? Because if it works inside this thing, then when somebody else comes and clicks on those things, it will work for them too. And I see this as a real big help for those people rather than like, okay, send me a zip archive of your M files. What are you gonna? Because that's about all they can do. They don't know what.
Okay, well, the next presentation is about industrial use cases, and here actually we can see some of those people that we've been working with in the past that had such problem, basically of like developing an application and afterwards deploying it from just a few experts to more widely within the company. So this is the idea. Shall we make a small break, or no? It looks like you're. It's okay. People come and go. It's free, so we're all free here.
Free. We got coffee.
Yeah, even with free coffee. So industrial use cases. This is I think we're a bit late on schedule, but it's all right. I mean, it's we have Q&A afterwards too. So industrial use cases. Here I'm going to keep this structure of like modeling and simulation, data analytics, and application development and deployment. Those three parts will be the frame of this presentation. So starting with modeling and simulation, and for each of those, I think I have like 3 to 5 slides. So the first one is coming from the automotive domain. Valeo is a French company providing a subsystem to the automotive OEMs. And here, basically, what they do a thermal pre-dimensioning from electronic circuits. They start from the 0D, 1D mathematical model and go afterwards to a more detailed 3D model and simulate CFD, like the thermal and computational fluid dynamics around it. So here, this is like the 0D model, let's say, and this is like the 3D model. Now, in early phase, what they figured out is that it's pretty effective for fast, quick iterations on the design before it's like stuck to one design. But after one question is also precision of that design. So they run both, like first starting with 0D and afterwards going to 3D. What they figured out is that with modeling, they end up having quite good prediction on the design even in early stage. So that's actually well suited for early stage of.
What is its x-axis?
X is
X.
It's t. It's a time over time. It's just a simulation over time of the temperature, and you see like over like more than 100 degrees Celsius. There's only like a few degrees of difference between the CFD model and the mathematical model. The second example that I want to take is from the French Space Agency. So they rely quite heavily on Scilab for their mission, and especially for one mission lately, they performed the mission Rosetta in order to land philae on the comet called Chury. Basically, here what you see is a cut of this comet. So they use Scilab for flight dynamics, and here one of the problem was how to land on the comet when you don't know what it looks like. I mean, it started like 10 years ago, this project, so it's pretty impressive. And when they went closer to the comet, they needed to compute the landing sites and also know how the comet will move. So this is also like some kind of mechanical flight dynamics. And those red spots that you see, those are this is due to the ray of the sun coming on the surface with ice. It's producing gas, so it's displacing the comet. So this is what they did with Scilab, and what they told us, maybe you've heard of it. The philae lander kind of bounced on the surface, so they said it's not due to Scilab; it's a mechanical problem. They're still happy to work with us. Eramet is a French large company in nickel and manganese. Those are some metallurgical reactions that they model in Scilab. So basics ODEs of the first order, and they use one of our solver for discrete and continuous states solving of linear systems. The Fraunhofer in Germany, it's a quite famous research institute, especially this one, the Fraunhofer EES. Those are the one responsible for the MP3. We're working with them. They do a lot of signal processing, image processing, and they developed a toolbox on Scilab for their polarization camera. So this is basically here a problem of polarizing glass, and depending on, here you have really nice colors, but this is not Picasso. It's just displaying the different angles of the lights and the polarization of glass. So this is a glass and this is a polarization. And the German Aerospace Center is performing model in the loop, software in the loop, hardware in the loop testing. So those are methods of testing embedded systems. It goes through code generation. So this is for flight simulators. They have a flight simulator that you see here from, they have two models. The first one is from Airbus A320, and the other one is an helicopter in the back, so they can switch the two models. And so basically they develop some of the subsystem of, for example, the A320 as a ground proximity warning system that is developed in Xcos, and they generate the code in order to run it on the simulator. So this is one of the subjects in modeling and simulation. So now we go through the use cases in data analytics. So in data analytics, one of the first example is from Peugeot, the French car manufacturer. Here they perform a lot of test and measurement from post-treatment of aeroacoustic data. This is just mirroring the impact of the rear mirror on the design. So basically, yeah, here you see they record all of those data from sensor. They go in the spectral domain into frequencies through a Fourier transform, and they just display the results on a small graph. Dassault Aviation is, as I mentioned earlier, is doing much more detailed analysis and post-processing in terms of design of experiment, DOE, design of experiment, and post-processing and optimization. So basically, they start from wing shape design. They perform lots of simulation in terms of fluid dynamic, for example, of this design. They gather all of the results. They go through correlation. They try to do some statistic correlation. They build some more detailed model in terms of learning from the data. This is a self-learning map, also called coherent neural networks. So those are neural networks learning on the data that were performed through simulation. And afterwards, they would try to optimize the design, optimize the input parameters in regard to the output of the simulation. So they perform kriging, you might have heard of, and also some of the multi-objective optimization. There's a lot of it in Scilab. Oh, speaking about also machine learning, so we were working also with a company trying to detect electrical arc, because this is like quite an important problem for them. Electrical arcs are starting fire a lot of the time, so they need to detect that and prevent that. There's a norm now for that. So we try to use some classification algorithm, either like logistic regression, but afterwards some more detailed like support vector machines and neural networks. So this was one project that we did with Scilab. And also some, this was one of the examples that I also mentioned earlier from the CNRS, French Research Institute, performing automatic detection, kind of pattern recognition basically on data captured by LiDAR. So they go with a plane and scan the land and try to detect those small dots, those patterns. It's completely not feasible if you try to look at the pictures and try to detect them. So and they like scan kilometers of square kilometers of land. So it's pretty useful for them. And here, maybe we'll say a few more words on that afterwards with Kunal on model reduction. So basically, here the problem that we wanted to address with those methods of model reduction was for vertical wind turbine. So in Belgium, there's this wind turbine company trying to deploy 10 to 20 wind turbines in the field. But the problem they faced is how do we optimize the positioning of the different wind turbines, not to impact each other and try to maximize basically the production of the field. So this is something that, like, done with a regular simulation in 2D or 3D, it would take ages on supercomputers. It's just not feasible. So you cannot try and use some different configuration and just launch such jobs on supercomputers. It's just not feasible. So basically, what we came up with is so we built a reduced order model from one of those turbines, and we used it as an input for the complete field simulation. And what it does from a mathematical point of view, it's reducing in terms of decomposition of time and space. So starting from a complete difficult Navier-Stokes equation, it's splitting the time component to the space modes. And this is actually what's performing afterwards reduction. So you just cut, just like a FFT, you just cut to the first modes, and you can capture like most of the information, but at really lower computational costs. So yeah. And so those were all the data analytics that I wanted to show you. Now the last aspect is application development. Starting with Ariane Group. So the Ariane Group was called before Airbus Group, and then Airbus Defence and Space. They're always renaming, but anyway, here for the design of Ariane 6, what they did in the early stage of the design, they created a small application based on Scilab for mechanical precising. So here, the problem that we're facing in early stage is how to design a rocket with only a few parameters. How do you iterate on the early stage, try to pick the element, the structural solution that you want to come up with in order to here minimize the buckling effect. Buckling is like when you apply pressure on a cylinder, how it's going to deform the strain and stress that will appear. So the small application that they developed in Scilab is implementing some algorithms that they developed on a series of thin plates, and it's in early stage before they go into a complete 3D modeling and finite element analysis. So it's being deployed right now in Ariane Group. Another aspect from ArcelorMittal of use of Scilab is here quite interesting. So they develop a lot of metallurgical models at ArcelorMittal, not only in Scilab, but in C, in Fortran. They have a lot of Fortran, in Python. And what they want to use Scilab for is basically as an orchestrator of all of those models. So I have like, at the moment, I think that 200 models from different research facilities, and they want to deploy it to the factories. So in order to do so, they use Xcos as a way to graphically, like chain the model. And it's independent. Basically, if it's a Scilab model or a Fortran model, you can just run the model and chain them, produce results for non-expert of the simulation, and deploy it in dedicated application, so that on the production line, those process engineers are really far away from all of the metallurgical behavior that is happening in those reactions. But basically, what they say is it gives to non-expert of the simulation a really powerful tool in order to perform simulation. EuroCFD is a small company in France, and they are working also with ArcelorMittal on a similar problem for modeling the corrosion that is happening. So some reactions that are happening in pipes. So here they use Xcos in order to drag and drop and build a circuit and have a model-based way of designing a circuit for their dedicated application on corrosion. the German Aerospace Center, once again, here it's mostly for image processing. So we were talking about image processing before. This is for infrared image processing. So they perform a lot of flight tests, and afterwards they gather the data and they want to, identify some. So here, just like removing some noise and enhancing the image and do some data processing. So yeah. There's much more to do with image processing, but they want to focus on that. And there's also some other department from the German Aerospace Center that are doing some flow cone analysis. They put some flow cones on the wings, they fly, and they try to look at the behavior of the flow cones in order to identify the turbulences on the wing, in order to give back those elements to like Dassault or like Airbus to iterate on the design. And the last example that I wanted to take is the one from Sanofi, so French pharmaceutical company, facing some problems in their factories on production line. It's for energy consumption. So they figured that energy consumption is mostly coming from HVAC, so heating, ventilation, and air conditioning. It's accounting for 50 to 60% of the cost. So it could be like $500,000 a year, just because of the HVAC. So they figured, there might be something to do in order to optimize that. So the first thing they did, they used Excel, and while it wasn't scaling that much, obviously, because first they started with Excel, big, huge Excel files. It was like 200 megabytes. It took 10 minutes to compute. It was just not maintainable. And they thought, okay, let's deploy this Excel file, because that's what people do. It's a good idea. It sounds like a good idea. So that's what they did. And then they figured out, we need to find another solution. So they came to us, and basically we took this Excel file, we made a Scilab application out of it. So separating the data from the algorithm and making a dedicated user interface to that. And this was the first step. And afterwards we deployed it to the cloud. And this is the application is called OptiClim. And now what they're aiming at is with deploying it on 120 industrial sites, production sites worldwide. They think they can save up to 10 million. So for them, it's like building up a new factory, basically, just based on those savings. So it's quite an interesting project. This is how the application look like in the Scilab Cloud. So I showed you like a very small and kind of stupid application. Now this is like a real serious application built on centralized data and models, easy use deployment, and flexible upgrade. It's producing some dynamic graphs, so they can just change the parameters of temperature, of humidity and stuff, and they can see directly what are the impact on the cost. And so this is what they do right now. They're deploying it widely through the industrial company. And well, that's about it. Afterwards, we have some references in different domains. Well, you will see mostly French names, but now we're actually trying to expand, thanks to ESI, try to go out of France. And so, yeah, that's it. Thank you.